let's talk about parametric surfaces, okay? And preview these kind of things, okay? So far, we have done quadratic surfaces, right? Z is a function of x and y, which is much simpler, but complexity of this thing, right? Yeah. Let's review what vector function was briefly before we start this thing. So if we have a vector function, let's say R, my favorite example, stairway to heaven. Say we have 2 cosine t with the I vector plus 2 sine t with the j vector plus t, k vector, right? Let's take a look at what that thing looks like. It was like this thingy except just skeleton. So let's go back to this and so we'll put 2 cosine t here, and then we'll go to delete all this. And oh my god, undo. Okay, there's always undo. And then 2 sine t. Okay, and I just put t here. Then this shows up. And we're familiar with this thing now, right? Stairway to heaven. I'm going to zoom in a little bit so you can see it better. That thing. Good. Now that has a 1 degree of freedom, right? Either you can move forward or backward, right? This is still one-dimensional figure. It's a space curve. And we have to give another degree of freedom, so we have 2-dimensional freedom and create that thingy. How can we do that? Right? So watch this. Instead of this, why don't I create a new vector function so that we can see both of them together? So that is equal to x, y, z. I'm gonna bring this thing down a little bit so you can see it. So instead of just 2 cosine t, I'm gonna do this. Open parenthesis and the 2. Then I'm going to put plus sine v, not there. This is such an inconvenient. Okay, there. Sine v, I vector, right? But times cosine u. Okay, I'm going to explain what's going on here. I'm going to go to next one. And here I'm going to put open parenthesis 2 and then plus sine v. And then outside of the parenthesis, really. Outside of the parenthesis, I'm going to multiply that by sine u. Okay, and the next one, I'm going to just put u plus now cosine v. Before I show you what this is, let's just review what this was. See, our u is same as our t up here. You know what I'm saying? So without v, if these v terms are not here, then it's exactly the same thing as a stairway to heaven. 1 degree of freedom. Okay? Imagine at some point on that spiral stairway, we fix u, and then let's just take a look at v. Let's just look at x and v. Okay? 2 gives us radius, right? At some point, we have now off from there sine v, cosine v. With a y and v, sine v, cosine v. Do you see tiny little circles? It's not easy to see, but why don't I show you that thing? I'm gonna put color. No, that's ugly. Better? No. Stripes. Do you like this? Or do you like this? Which is better? I'll say whichever you want to the note. Wow, you kids are really not interested in any of this now, are you? Okay, I'll just save this then. So our usual vector function is inside. This is a good shot. And then we have given another degree of freedom. So if you look at the cross section here, see those are tiny circles between, this is X and Z. And when we move over here, somewhere the cross section between Y and Z. You know what I'm saying? I think this is the best angle right there. Okay, let's save that shot. And then update our note. Instead of that, I'm gonna put, oh, that's big. Okay, so now I'm gonna write this down and let's talk about it, okay? So the vector function in parametric surface, this is a parametric curve, isn't it? Vector function is parametric curve x, y, z. Maybe I should write that down as well. So vector function was just this thingy. This is x sub t, I vector, and this is y sub t, y of t, and then this is a z of t times k vector, isn't it? Oh, did I meant to put t here, okay? So we're going to do a similar thing with parametric surfaces. We'll have some kind of vector function which has u and v in it, two variable functions, so it has a 2 degrees of freedom. And generally it's going to look like some x, 2 variable function, u and v. Our x here was the 2 sine, well, cosine u and 2 sine v. You get it? With the I vector plus some y with a 2 variable function uv in it, with a j vector plus some z with 2 variable function in it, uv. So instead of using t, they tend to use u and v here. Okay, this is what it looks like generally. So in this case particular, our vector function was, okay, I'm gonna write it like this. Here is cosine u I vector, and then sine u j vector, and then here's u, right? K vector. If I write it like that, that's same thing as these guys, right? Well, I have to put 2. So let's put 2 here and 2 here, and right, space, not the space. So this is the same thing as that thing now. But I want to give another degree of freedom, which is this circular looking thingy. So here I'm going to put sine v here, like that, and another sine v here. So there's no circular motion between x and y. And then this one, I want to make it a cosine, so 2 plus cos, yeah, u plus cosine v, like that. And that creates this vector function, which is parametric surfaces now instead of curve. Okay, right now it's not really sinking in. And then I could have easily used cosine here and sine here, and it would have worked exactly the same way. Okay, so this is parametric surfaces. Are you scared yet? Okay, let's back up and take it easy from the basics, shall we? Okay, now, so let's do an easy one. We're gonna come back to, we'll create this, but let's just shove that to the side. Say there is a 2 variable function. Say there is something like Z is equal to some quadratic surface, X and Y. And concrete example of that would be, I'm going to put it here so you can compare it side by side. X squared plus 4y squared, our paraboloid. Can you imagine what that thing looks like, the paraboloid now? Okay, now how can I parametrize this? A little closer. Okay, so what we can do is, I'm going to do this one first. We can just say X is U. It's same as we parameterize any function with a single variable. Y is equal to V if it's a nice simple vertically function. And then Z is equal to X squared plus 4y squared. So you can put U squared plus 4V squared. Would that work? Let's find out. I mean, we got this thingy. So let's get rid of our vector function now. I'm going to delete this thing. And then here, I'm going to put just U. And here, oops, I'm going to put just a V. And I'm just going to put exactly what we had, which was U squared plus 4V squared. Ready? Okay, it's only showing you part of the parabola at the moment, but that's because of this parameter setting. U is running from 0 to, so I'm gonna go this thing and this thing start from -7, and V start from -7. We need positive and negative side. Let's see. See our paraboloid. I'm gonna zoom in a little bit, but zoom out, zoom in. So you remember this? Oh, this. Do you remember paraboloid? It looked like this, correct? I guess I will zoom the other way. Right, how about that? So it creates exactly the same parametric functions that we are used to. Good questions now before I do something a little more complicated? So we don't have to save this, I guess. Okay, let's go back to the notes. So bring it down a little bit. The vector function, if we want to write it as a vector function, it'll be like this. R of two variables, U and V, it's just that thingy, U, I vector plus V, J vector, that thingy, and Z is equal to plus U squared plus 4V squared, K vector. You know what I'm saying? Okay, so let's summarize this thing with, well, generalize this for any quadratic surface, any function of Z, right? Two variable function Z. We can do the same thing because this skill is critical because later when we have to find the surface integral and you need this vector function, two variable vector function, okay? So we can write this as X is U, Y is V, that X looks ugly. And our Z is equal to still function of X and Y, but now it's U and V. So we just make that switch. So our vector function with the UV, which used to be simple quadratic surface, is just X I vector, well, U I vector plus V J vector plus your F of, I need a little more room. Oh, why don't I move this thing over? F of that same thing, X, Y, but now written as UV and K vector. That's generally how it works. So this much is pretty easy now, isn't it? Say yes. Okay, now we're going to create this ellipsoid. Okay, ellipsoid, we know the equation of the ellipsoid, but that's not a simple function of X and Y now, is it? right? So how are you gonna do that? Okay, this one we have to be a little more clever. And brilliant suggestion before I start writing. It has to do with coordinate transformation. Okay, sometimes if you use different coordinates, such as spherical coordinate, it tends to do wonders. Okay, what was x in spherical coordinates? Somebody tell me. Rho. Oh no, you don't remember any of this. Now the truth comes out, right? You are just Nick. It was rho sine phi cosine theta, right? So let's say the x radius here is 4. And then we want to have sine, instead of phi, we'll just put u, because we're using u and v. So we are using phi and theta as our variable. You get it? You can use phi and theta, no problem when you're doing calculus, but this program only uses u and v. So sine u and then cosine v. You know what I'm saying? And then y, let's say same.
Sine theta cosine phi.
Sine phi cosine theta. What did I say?
Wait, I can look it up, but for some reason I thought it was sine theta.
This is phi, this is phi, and this is theta. It's a cosine theta sine phi. I usually put phi first. So it's like sine phi cosine theta.
Oh, okay.
And this one was sine phi sine theta, wasn't it? And this one was rho and then cosine. Rho cosine phi, correct? Let's make this side longer so it becomes an ellipsoid. So this is cosine. You know what I'm saying? Well, one way to find out, right? We'll test this. Okay, we go back here now. So I'm gonna put here 4 sine, what did I say? Sine u. Oh, I have to put parentheses around. Shoot. This thing is gonna act up. I'm gonna do it this way. Oh, there. Cosine. Yes, see, it does that. This is so annoying. Delete this and then put u here. Did that work? Nope. I'm afraid I might have to retype this whole thing. Yeah, I was like 4 sine u, and I'm going to delete this part. Okay, that one now, whoops. I'm going to start with a parenthesis and then put 4 sine u here, exit parenthesis. It of course goes to the next line. Why wouldn't it, right? Why would this thing make my life any easier? And then sine v, and go to the next line. Whoops. God, this is such a user-unfriendly program, but it graphs well. So it was 6 cosine u. Ready? Moment of truth. Look at that, huh? Ellipsoid. You know what I'm saying? What color do you want? Whoa, like this? Nah. Somebody's having arms up. No, that's ugly. Nah. What is wrong with this mouse? How do you like this? But you can kind of see, if I have this thing, same as other, then this will give us a sphere, right? Because that's exactly spherical coordinate with a radius 4. You know what I'm saying? But now I can make this thing, let's change this, so make it longer this way, or I can make that shorter that way, let's say 2. But I can change one of this and make it long that side. You know what I'm saying? So any control is possible in any direction. Remember when we were doing the parametric equation of ellipse, then you can adjust the major and minor axis by just adjusting that number in front of cosine and sine. It's kind of like that, but this is a 3D. How do you like it? Okay, are you guys there? Can you hear me? For some reason, my network, I almost got cut off. Huh. Okay. So I'm back. So let's go back and try to finish this video before something more bad happens. So putting it together as a vector function, now I can write it as R of UV is just that thingy, the x component for sine u cosine v with I vector plus 4 sine u sine v with a j vector. I'm going to put this thing up there higher, and then plus 6 cosine u with a k vector. So mainly you have to work with either this kind or this kind. There isn't a whole lot that you have to do. It's not like you have to come up with this on your own, most cases. But whenever you see these two variable parametric surface functions, you have to recognize what it is by looking at it. Okay. How can we achieve such a thing? This is a very circular thingy now, isn't it? So let me rewrite that thingy. So z squared plus 1 is equal to x squared plus y squared. It's a hyperboloid, correct? Of one sheet. Okay then. Now, how should we parameterize this? Let's be clever about it. Because one way is just put x for u and y for v and then z squared. That's ugly, right? So between x and y, we see circle, correct? Let's just think about, let's say, forget z for now. Z is some constant, right? So if we are just parameterizing this, x squared plus y squared is equal to some constant. How'd you do it?
You would do r cosine theta and r sine.
Yeah. Well, c squared, right? C cosine theta plus I vector plus c sine theta j vector is how you'd have done it, right? So we get that idea. So that's great. Okay. Well, let's forget y for now, right? And then just look at x and z. Do you see that x squared minus z squared is equal to 1? Right. Do you see this thingy between x and z? How would you parameterize this then? This is the very first lesson I taught you at the beginning of the BC. There are two different ways to do it. At least if you can come up with one of the two, I'll be very happy.
You can isolate z and just do x is equal to x and y is equal.
Oh, let's not do that.
Okay.
Let's not do that. I mean, that could work, but let's not do that. Because we don't want plus or minus business, right? The whole idea of parametric function is to avoid plus and minuses, right? So what would be a nice parametric equations that gives you hyperbola, the name hyperbola? Okay, option 1, there's a trig function. Option 2, the hyperbola. Something square minus something square is equal to 1. Well, do we know any trig identities as something square minus something square is equal to 1? What is it?
Secant and tangent.
Secant and tangent. So what we can do is x is equal to secant theta, and then z is equal to tangent theta. That'll do it. You know what I'm saying? What's option number 2 then? What can be better than this? Oh, you haven't learned the hyperbolic functions, hyperbolic sine and cosine, have you? I never mentioned that in this class. The other option is this, e to the t, or theta, t, plus e to the negative t over 2, and z can be e to the t minus e to the negative t over 2. This is known as a hyperbolic sine and hyperbolic cosine, and this thing gives you hyperbola. You wanna see why that is? Well, is this one at least obvious that gives you hyperbola? Or you want me to show you? Okay, assuming you can see that, maybe we'll just go with this. But this one, why would that give you? Well, let's just compute x squared is equal to denominator 4 e to the 2t plus 2 times this times that. Is that just 2? Plus e to the negative 2t. Good. And then z, I keep forgetting this is z. And that's likewise e to the 2t minus 2 plus e to the negative 2t over 4, isn't it? Then if we subtract vertically, I'm going to push this guy down. If we subtract vertically, then what happens? Then we get x squared minus c squared is equal to, this 2 cancels, that becomes 4 over 4. This 2 cancels, so bang. How about that, huh? That's very nice now, isn't it? Well, then the question is, why would you want to do such a thing when you have these two? This thing does the job. So why would people, mathematicians being who they are, they created this and they call it hyperbolic sine and hyperbolic cosine, because behavior of these things, derivatives and all, is very similar to regular sine and cosine, where regular sine and cosine gives you an ellipse, as we saw earlier, and this thing gives you hyperbola. But why? What's the motivation of having this thingy, which looks complicated, when we have secant and tangent, which are very nice functions? Or are they nice functions? Can somebody give me the motivation behind coming up with such a thing instead of using these two? Because people, I've never seen anybody using this. This is just like something I came up with in BC class. Everybody uses this. But why? Why would you want to use that thing? Somebody give me a good enough reason, or at least a motivation. Definitions do have motivations, people. There's a reason they came up with such a definition. So we cannot just say, oh, because it's a definition, right? Somebody created it for a reason. What is the reason? Okay, generally these conics are used in planetary motions, correct? Orbit of the planet, satellites and stuff, right? And then this is the calculus, which means we have to take a lot of derivatives, right? These two are not nice functions. Number one, they have vertical asymptotes everywhere. Number two, their derivatives are very nasty, right? Derivative of this is secant times tangent. So what's the second derivative? U. Derivative of this is a secant squared. So what's the second derivative? You see what I'm saying? So this is not preferred function for hyperbola. Derivatives of e to the x is a very, very nice. You can generate this forever. You know what I'm saying? So people prefer this so much more over this. But if you want to, we can use this. Because for our purpose is to generate this hyperboloid. Okay, so now let's put these together, okay? I'm gonna erase all of this now. Maybe I should have written it neater and save it as a part of the note, but hey, too late now. Okay, they're gone. We have to write parametric equations between x, y, and z. I'm gonna write it separately. I'll write neither this time. X is equal to something, y is equal to something, and z is equal to something. Okay, now let's just think about x and y first. It was a cosine and sine, right? And radius in at xy plane at least was 1. Correct, when z is equal to 0. Okay, let's just think about that. So maybe we should start with cosine u and sine u. Okay. Then let's just think about x and z. How do you want to do this? Let's just go with a secant and tangent. Seems easier to write. Should we just attach it like this? Would that work? Can this scheme possibly work? Wait, what about y and z? It has to be the same hyperbola, right? How about that? What do you say? Can this work? One way to find out, right? Okay, new calc. Are we glad that we have this thing that graphs this for you? Okay. Let's graph it. So I want to graph three-dimensional vector. Three-dimensional vector, I said. My keyboard stopped working. Really? Oh, God. Then it worked many, many times. Three-dimensional vector is equal to another three-dimensional vector. So I want to put, oosh. Are you guys there? My screen just went blank for some reason. Oh, whenever we are doing recording, this has to happen, of course, right? So this was cosine. What? It just crashed. Of course, when we are doing recording, this has to happen, right? Yeah, let's start over. Dang it. Three-dimensional vector is equal to another three-dimensional vector. Move that pad away here. So this is cosine u. I regret not putting parentheses. Okay, Okay, start with a parenthesis, otherwise it's going to give me some weird thing. Cosine u, and of course I have to go back here. Okay, times sine u, I mean secant v, and here then I'm going to put here sine u, and then go out here, not there, here, here, and then secant v, and then z here, I'm gonna put tangent v. Moment of truth. Ready? But that didn't work, you're saying, right? Hold on, hold on. Let's vary these things from 2 pi, right? So to 7. And 7. Oh, that worked. Look at that beautiful hyperbola, hyperboloid. Do you love it? What is there not to love, right? Amazing, isn't it? However, that's not all of it. We have to say this thing lies to the right of the xz plane. What? So we want to cut this thing in half. I'm gonna zoom back out. Here's the x-axis, z-axis here. So I want this half, not that half. Somebody, and so which means we have to adjust the domain of this parameter. Somebody suggest how we can do that. This is a great way to feel this. Which parameter, u or v, do we adjust and cut it? And by what?
U.
U, okay, it has to be u because it has to do with x and y, right? And u from what to what?
0 to pi, because that would
0 to pi is good. Can I do pi here? Nope. I guess 3.14. We'll have to approximate pi. Ready? That didn't work. Why didn't work? Why didn't it work? Huh. Does it have to do with this v? Let me cut this in half and then let's see if that worked. Oh, this v hyperbola. Oh my god, it goes to the other side, huh? Dang. I did not expect this, right? This scheme worked except if the v, because v, it can go both sides, so maybe we shouldn't have used tangent, eh? Tangent can be positive, negative, so it goes on both sides. Do you see that? Oh, wow. Should we go back and change this thing to hyperbolic sine and cosine? But then you didn't know that, so it's not fair to just throw that at you. You want to see it anyway? Yeah, let's do that anyway. So we back up and then we regret using secant and tangent. More the reason to use hyperbolic sine and cosine, right? So we'll go back up this and we'll put hyperbolic cosine here, which is e to the v plus e to the negative v over 2. And same thing here, e to the v plus e to the negative v over 2. And here we put e to the v minus e to the negative v over 2. Okay, and let's see if that works. Oh, this better now, right? Okay. So we go back up here. Let me start editing this first. So open parenthesis, E exponent, V, come outside, minus E to the negative V, then come outside one more time, divide by 2, and hopefully I can copy and paste this. Paste this and change that to plus sign. Okay. And then I will copy and paste this whole thing. Of course, it's not going to let me have it that easy. Okay. Now this is going to work. So I can change that back to no restriction. Oh, do you know why this is only showing up on top? Because I didn't give the negative value. So V can now vary from, let's say, -7 to +7. Now you see that half of the. Okay, that's kind of big. Let me change the Z value to, oh, not that, -2 to +2. So we have a reasonable looking half of a paraboloid. That was amazing now, wasn't it? Right, more the reason to use hyperbolic function for paraboloid instead of secant and tangent, because secant and tangent is unpredictable. This is a great shot right there. I'm gonna tilt it a little more. There. Rotate it slightly more. Yeah, I'm gonna take that and save it to the note. Okay. Oh, we still have to create a vector function, don't we? Let's do that. Did we have to create a vector function? I will anyway, but that's the picture. Okay, so if we want to have a vector function, that vector function should be R of a UV, and then just these guys, right? So let's write this, I'll just write it. Cosine U of e to the v plus e to the negative v over 2 with the I vector, and plus sine u, and then e to the v plus e to the negative v over 2 j vector, and finally plus parenthesis, I don't need a parenthesis, e to the v minus e to the negative v over 2 k vector. And then we want to limit the domain of u from 0 to pi. And that's this thingy right here. Oh, that was a beautiful, beautiful example now, wasn't it? Okay, let's go on. Okay, can we top that? Part of the cylinder that lies between x is equal to, this one is easy now after that. This looks so easy now, doesn't it? We just write it. What's x, y? It's between y and z, correct? So how do you create a circle between y and z? I will leave this thing off. So it's just cosine and sine, isn't it? Which one do you want it to be cosine? Y or? Okay, fine. X, Y, Z, Between y and z, which one do you want it to be cosine and which one do you want it to be sine with the radius 4?
I guess y sine and z cosine.
Okay, so this is cosine then, like that? You want u? It doesn't matter. Like that. What do you do with x? Because we want to give x another degree of freedom. This is restricting y and z. X has to vary. How's that? It has to be a different variable because you don't want it to vary with the y and z. Then it creates this vector function, space curve, right? We want space surface. And this, we need to restrict it, right? So your v needs to be from 0 to 5. You get it? And then u can go from 0 to 2 pi, I guess. But even if you have it go unlimited amount, it doesn't care. It'll just go wrap around many, many times. So now we can write this as a vector function. So your r of uv, you see how to come up with a vector function, right? You just come up with parametric and then you write it as a vector. So this is v I vector plus 4 cosine u j vector plus 4 sine u k vector. How about that? Oh, that was beautiful. Not as beautiful. And after that hyperbola, everything looks so trivial. Okay. Let's look at number 34. Okay, 34. We want to find the equation of the tangent plane at x is equal to what? How are we going to do this? Because it doesn't look like we can even eliminate this thingy. At u is equal to 0 and v is equal to pi, but how does that? Let's take a look at it. I wish I could look at the problem and do this. I'm going to display the problem on my screen on the other computer. This is number what? 34. Because I need to look while I type this in. I cannot keep going back and forth. That creates a terrible video. Okay, so we're done with this, right? Okay, so I'm gonna retype these equations now. So your x is equal to uv. Oh, just delete the whole thing and start over. X is equal to uv and y is equal to u sine v. And z is equal to v cosine u. And I'll give these guys more freedom. Let's say that starts from 0 to 2 pi. Now let's just go have it go up to 7. Whatever that is, right? Holy cow, right? Look at that thing. Seven is too big. I'm gonna cut it at up to pi, so let's just go up to 4. Right? So it still has 2 degrees of freedom. And it just spirals out. So no wonder we couldn't see this, right? Okay, now we'll go back. So knowing what this thing looks like, I don't think I even want to make a copy of, should we? Just for the fun of what angle is the best? So hard to control. I guess that's the best angle, right there. Tilt it a little more up. Yeah, that's a great angle. Okay, I'm gonna make a copy of that. Move these parameters over here. You know, I'm totally trying to buy time, right? Okay. Now, wherever, let's just say at some point we want, let's say that point is somewhere here, right? And we have to put this thingy down. How can we put a tangent plane on something? In order to have a tangent plane, somebody say, what do we need? We need a point, and because we have a point, we can compute the point by substituting this 0 and pi. What do we need other than the point?
The normal vector.
Normal vector, let's just throw it here abstractly. Let's say that is our normal vector. That's a great looking normal vector, isn't it? Say that is n. How are we going to come up with a normal vector now? Okay, I'm gonna write point first. Point, of course, is easy. That is r of 0 pi, right? So let's get that point. And if you have 0, this thing is 0, right? Let's write it as component notation. So 0 and u is equal to 0. And pi, if you plug in pi, so this is the only thing. Cosine 0 is 1, so 0, 0 pi is our coordinate, isn't it? So on reality is somewhere on this z-axis, but we don't care. This thing looks cooler, so we're keeping this picture. This is generalizing. It's an abstract picture. Mathematicians love abstract pictures. How do you create the normal vector? That's ugly n. I'm open to brilliant suggestions. This has to do with when we are doing surface integral and we parameterize and blah, blah, blah. That the formula for the surface area, that ds, when we did the ds calculation, we kind of used that technique.
Crossing drd.
If we take a derivative will be tangent to this thingy. You know what I'm saying? So if I take a derivative with respect to u, it'll be whichever is the u direction, which we cannot see, but it'll be tangent to that surface at some direction. If I take a derivative with respect to v, that also will be tangent in some other direction. We don't care. All we have to do is to cross the two. You know what I'm saying? Then that'll definitely give us normal vector. How about that? Wasn't that great? So what we have to do is we have to take a partial derivative with respect to u first and with a v, and then we're going to cross them. So with respect to u, we are going to have v I vector, and this one is plus sine v j vector, and then cosine. So we have negative v cosine negative v sine u j vector, k vector. Good. Say yes. Okay. Now we're going to evaluate this, take the partial derivative with respect to v. So v will have u vector plus, and then here with respect to v, so we're going to have plus cosine u. I think I screwed this up. Let's go back. If I take a partial derivative with the no, I didn't screw up. I screwed this up. So this is going to be u times cosine v, j vector. Good? Say yes. And then k vector with respect to v will just be plus cosine u, k vector. So far with me? And you're saying, wow, we're going to cross the two, that's horrible, right? Well, that is if you want the general equation of the tangent plane at any point, but no, we don't even care. We only need it at that point, correct? So substitute 0 and pi for u and v, okay? And we'll do it that way. So my partial derivative, and you're gonna hate this notation, 0 and pi, like that. Mathematicians use this kind of notation all the time. So 0 and pi, so we'll just do it with a coordinate pi, and sine pi is 0, eh? So we have 0, and this is u is equal to 0, so that's 0. You with me? You with me? And then second one, with respect to v as 0 and pi. So I'm using this as a function notation. I know, don't you hate it? I hated it first when I saw it, but it's such a convenient thing to have. So this is 0 now, and this is 0 again, and you put pi here, cosine pi is -1, and we only need to cross that. With me? Okay, so our normal vector is this thingy cross this thingy. That didn't show up. Okay, let's imagine I, j, k there. So I, 0, k, j is a -1, so we have pi. Good. Say yes. And then k is 0. So we just have something in y direction. Good. Let's go back to our grapher and see why that is. Let's try to understand why do we have something only in y direction. Okay, I need this is y axis, isn't it? That was x-axis. Now we are trying to find the tangent plane right on this, somewhere at pi, right there. Of course, that tangent needs to be on this thingy, so our normal vector will stick out in y direction. You get it? Do you see that? Ah, wow, these are great problems. How come nobody ever asked me this before?
On the solution manual, it says -pi in the j direction. Yeah,
but it doesn't matter. That depends on which one you cross first. Because tangent plane, it has two normal vectors, right? Yeah, so then we really don't care. And we don't even have to use pi. We can just use 1, right? Right, we can normalize it because this is just the length giving the direction, right? So we'll use using n as 0, 1, 0. Right, that's so much more convenient. So last thing we have to do is remember what the equation of the tangent plane is. The equation of the plane is in general. I'm going to do this in blue. What was the equation of the plane? It has to do with n and then dot product. What do we dot this thing with? Ah.
So point it gives you? Or did,
Yeah, let me abbreviate it like this. What? What do you mean, right? Okay, so we'll use 0, 1, 0, dot that where this means x minus your, where's our point? Here, that the, you know what I'm saying? That's our point. That's what R naught represents. So x, y, and z minus pi. Wait, let me just make sure I copied it. Yeah, pi. Good. And so we have, wow, everything here is dies, right? So we just have y is equal to 0. Will that work? Well, we have to confirm it, right? We have all this thing. So I'm going to enter a new equation. And the new equation is y is equal to 0. Ready? Bang. Oh, that is a tangent now, isn't it? What color do you want this thing to be? You. I guess good old reliable yellow. You see that's a tangent right there? That's amazing, isn't it? I'm gonna take this. I think this is the best shot right there. And move the parameter over here. Okay, I'm gonna say this. Where is a good place to, I'll clean it up later, I'll just save it here.